Hello ladies and gentlemen, this is Dean from Multiply, and this is Linear Algebra. In the last video we explained vector spaces as being planes, volumes, four spaces, and so on, but there are other types of vector spaces as well. Before we look at them, there's an important property of vector spaces called their dimension, and we've mentioned this before when we described a plane as two-dimensional, the vector space is zero-dimensional, or Rn is n-dimensional. The dimension of a space is equal to the number of vectors in its basis, not the number of components in a given vector. So Rn, which we have described in the vector spaces video, as the standard basis spanning the space, so it has n vectors. Applying n is equal to 2, we have R2 is equal to E1 and E2. R3 is equal to E1, E2, and E3 for n equals 3. And you can extend this to R5, R28, so on. And it quickly becomes apparent that Rn is proven to be n-dimensional given by dimension of Rn is equal to n, or dim Rn is equal to n. As for other types of vector spaces, we're first going to look at the column and row space of a matrix. These are defined as the actual columns and rows of the matrix assigned as vectors and their spans. And while it may look obvious, there can be some things to trick you. Namely, if you were to ask to find the basis of column A, you'd first have to reduce the matrix and check the independence of the column vectors. Similarly, row A needs to be checked, but by first transposing the matrix, and we'll look at that pretty soon. In fact, since Gauss-Jordan elimination is done using rows, the row echelon form of a matrix can be thought of as an element of its row space. As the basis of either space is found by reducing the matrix, the dimension of column A and row A should always be the same. And here is proof, or not proof, but an example of what you would do when you have linear dependence. The next space requires that you remember when we talked about points on a graph as vectors. Well, what about when you have a curve? More specifically, polynomials. You can actually think of curves as vector spaces defined by the vector x f of x. And each of these spaces will have a new standard basis as well as other types that you'll need to solve for. So when we're looking at a polynomial space, instead of Rn, we use Pn, as in polynomial. The general vector, that's in air quotes, in Pn is given by f of x is equal to a plus bx plus cx squared, so on up to psi x to the n minus 1 plus omega x to the n. I've used psi and omega here because they're the last letters of the Greek alphabet, not because they're some defined position. Therefore, a general polynomial can be expressed as a linear combination r of 1, x, x squared, x3, x cubed, that is, all the way up to x to the n minus 1 and x to the n. So that these define our basis vectors. Again, vector in air quotes, although you can express it as a coordinate vector, which we'll see in a second. Since all powers of x up to n are included, even 0, the dimension of Pn is equal to n plus 1. Now, given some other conditions, this can be different. Say a subspace of Pn is defined such that f of 0 is equal to 0. In other words, this runs through the origin. Well, here, any combination of positive numbers of x will work, as the coefficients are multiplied by 0, but the constant term has to remain constant. It doesn't have a 0 multiplied by it. And therefore, the only way to make this 0 is if a is 0, but if a is 0, then it's a combination of all the other vectors, and therefore the 1 is omitted, and the basis becomes just n. Or the dimension becomes n, and the basis becomes x, x squared, x cubed, so on. Another example is when you have v as an element of, these should be subspace symbols, sorry. But v is a subspace of P2 and is defined such that f of negative 4 is equal to f of negative 5 is equal to 0, meaning that negative 4 and 5 are roots of the function. If you know some graphing tricks, you can tell that the only functions that fit this are multiples of x plus 4 and x minus 5. So the basis of the vector space is just x squared minus x minus 20, the product of those two. Now this is one polynomial. And so although we have the three basis powers of x, this is just the one coordinate vector here. And we have that v is equal to the span of 20, -1, and 1. Therefore, since it is just one vector, this is one-dimensional. To prove this, we can look at a graphing calculator. And here you can't really see it. If I do that, yeah, you can see here I have these two equations put in. And right now they're all equal. But if I set C to play, then you can see that as it moves, these 2 points, which are the roots at, stop please, at -4 and 5 never move. Similarly, if I set A and B to play, and they are now moving around, these remain on the roots as well. So we have proof then that this is the basis. To finish up with polynomial spaces, we'll look at when you have multiple values that are all equal, but not to a specific number. For example, we have V is a subspace of P3, such that f of -1 is equal to f of 0 is equal to f of 1. Here we're going to construct some general functions, general polynomials, that is. So for f of -1, we have this reducing to a minus b plus c minus d. For f of 0, we just have a. And for f of 1, we have a plus b plus c plus d. And now we want these all to be equal. That is the restriction. So a good way to solve this is to make it a system of equations and put it into a matrix and reduce it. However, the augment can be a little tricky. And we've set the augment to be 0 here, because if they're all roots, they're all equal, and it makes it easy to solve. But keep in mind that this doesn't mean that the constant term is omitted like last time, because we haven't defined a value that they're all equal to. Solving this gives that a is equal to 0, b is equal to -d, and c is equal to 0. D then is the free variable, and c is actually omitted. However, we keep a, as I just said. In the solution, then, this becomes the span of 1, 0, 0, 0, and 0, -1, 0, 1, which corresponds to f of x being a plus d times x cubed minus x. And again, if we look at this in the graphing calculator, here are the functions. And if I set both of these to play, and look at this, you can see that these points of intersection are always horizontal, which means they're all equal. And this satisfies the relation given that a and d change. So in general, a good idea is to look at the generic polynomial, and you should get an idea of how to do it. The last space isn't as in-depth as Pn, so if Pn seems like a lot to you, you don't have to worry. Next, we're going to look at m by n of r, which is a very messy way of saying that it is the set of all real matrices the size m by n that satisfy some restriction. The standard basis here is similar to Rn because we have e's again, but this time it's capital and they have 2 coordinates. These mirror EI in that they are matrices that just have 1 entry, a column vector actually of EI. However, this is a little bit different because EI would appear in the jth place as well. So you have that extra dimension of complexity to it. Therefore, since there's a matrix E for every entry, the dimension of M is Mn, or n squared if the matrix is square. And the basis of a subset of M is a little different to solve for because you have to think about it, and there isn't necessarily a good way to do it mathematically. So let's look at these symmetric matrices as an example of finding the basis of M 3 by 3. Remember that symmetries are just mirror images when you're talking about matrices. So we'll start this by looking at the diagonal, which can be any numbers. This gives us that the first three base matrices are just E11, E22, E33. And these are going to work similar to vectors in the sense of their linear independence. The rest of these entries then are defined by being equal to their mirror. So we get the other three matrices like this, and I'm not going to read all those out. So now we have 6 matrices that are all independent, and they give us a basis for symmetric matrices. Therefore, we say that the dimension of the symmetric subspace of M 3 by 3 is 6. There are spaces of matrices which involve matrix multiplication, which we haven't covered yet, so we'll talk about them then. However, like I said, if you're ever stuck on finding a basis, try making general vectors or general matrices as we did back here, and it'll help out a lot.